If you've ever searched for gold, you've probably been taught to look for obvious signs: quartz veins, iron staining, exposed bedrock, bright colors in the rock. But here's the problem. Most of the ground that actually holds gold doesn't announce itself. It doesn't stand out. It doesn't look exciting. And that's why it gets ignored. Today, I want to show you why the quiet geological clues matter far more than the obvious ones, and how experienced people miss gold simply because they're trained to look for the wrong kind of signal. This isn't about spotting something flashy. It's about understanding what nature does when it stops drawing attention. By the end of this video, you'll know what to notice when nothing looks special, and why those are often the places that matter most. Most people enter gold country already searching for contrast. They expect something to jump out at them: a sharp color change, a vein cutting through rock, a dramatic exposure that looks different from everything around it. That expectation shapes every decision they make. If nothing stands out, they move on. What they don't realize is that gold is rarely found because something looks different. Gold is found because something behaved differently, often quietly over long periods of time. Nature doesn't always mark those moments clearly. In fact, the most important geological clues are often the ones that blend in. Quiet ground doesn't mean inactive ground. It often means settled ground. And settlement is where gold belongs. One of the biggest mistakes people make is assuming that obvious signs are reliable indicators of value. Quartz is obvious, iron staining is obvious, broken rock is obvious. But obvious does not mean important. Those features are common. They exist in countless places where no gold ever settled. Quiet clues, on the other hand, are rare. Not because they don't exist, but because they're easy to overlook. They don't shout. They require interpretation. And interpretation is where most people stop paying attention. When experienced prospectors miss gold, it's rarely because they failed to notice something dramatic. It's because they dismissed something subtle. They looked at ground that appeared uniform and decided nothing happened there. But geology doesn't work in dramatic moments alone. It works through small changes, repeated over time, a slight reduction in slope, a minor widening of a channel, a gradual change in sediment size. These are not exciting to look at, but they are decisive. Gold responds to those changes far more reliably than it responds to visual drama. Another reason quiet clues matter more is because gold doesn't behave like most materials. It doesn't move easily. It doesn't float. It doesn't spread evenly. Once gold finds a place where energy drops enough for it to settle, it tends to stay there, even when everything else continues moving. That creates locations that look completely ordinary on the surface, but have a very specific internal history. Most people never learn to read that history. They're taught to hunt for features, not processes. They're trained to identify what looks like gold country, not what acted like gold country. That difference is critical. Quiet clues are not things you spot instantly. They are things you notice when you stop rushing to judge. One of the most powerful quiet clues is consistency. Not visual consistency, but behavioral consistency. When material size remains similar over distance, when gravels are evenly packed, when layers repeat without interruption. This kind of ground looks boring. People assume nothing happened there. But consistency often indicates long-term stability. And long-term stability allows heavy material to accumulate. Gold needs time. Quiet conditions give it that time. Another quiet clue is absence. The absence of large cobbles, the absence of angular rock, the absence of chaotic layering. People look at these areas and think material moved through too fast. In reality, absence often means sorting. Nature removed what didn't belong there. Gold, being heavy, was left behind. Quiet ground is often clean ground, and clean ground is often productive ground. But because nothing stands out, people don't stop. They associate effort with excitement. If something doesn't look interesting, it doesn't feel worth the work. Gold doesn't care how something feels. It responds to physics. Another subtle clue people overlook is transition, not contrast. They look for sharp changes instead of gradual ones. But gold doesn't require sudden shifts, a slow narrowing of a creek, a gentle change in gradient, a subtle difference in sediment rounding. These are easy to miss unless you're actively looking for them. And most people aren't. They're scanning, not observing. Quiet clues require observation. Another reason obvious signs fail is because they attract attention. Everyone checks them. Quartz veins get sampled repeatedly. Exposed bedrock gets worked over and over. Quiet areas get ignored. Gold often survives where attention doesn't linger. That's not coincidence. That's human behavior interacting with geology. Gold doesn't hide intentionally. People just don't look where nothing calls for attention. Another quiet clue is compression. Tightly packed gravels, hard layers beneath loose material. Resistance when digging that doesn't match what's on the surface. These are physical clues, not visual ones. You don't see them until you engage with the ground. And many people never do, because visually it didn't invite them to. Quiet clues often require contact, touch, digging, testing. They don't reward quick glances, they reward patience. Another angle people miss is that obvious signs often reflect source, not deposition. Quartz veins may indicate where gold originated, not where it ended up. Iron staining may show oxidation, not accumulation. Gold is rarely where it was born, it's where it was dropped. The reason quiet geological clues matter more than obvious signs is not because obvious signs are wrong. It's because obvious signs are late. By the time geology becomes loud, the system has already revealed itself to everyone. And gold, by its nature, does not reward crowds. Quiet clues exist earlier in the story. They exist before excitement, before disturbance, before repeated testing strips the ground of its easiest value. This is why experienced prospectors, even very skilled ones, still walk past gold, not because they lack knowledge, but because experience can harden expectations. Experience trains the eye to look for patterns, but it can also train the eye to ignore anything that doesn't match those patterns. When someone has spent years finding gold near bright quartz, iron-stained gravels, or classic textbook locations, their mind starts filtering out anything that doesn't fit that picture. Quiet clues don't announce themselves as gold indicators. They appear as small irregularities, minor inconsistencies, subtle deviations from what looks normal. And the mind, especially an experienced one, is very good at dismissing those as noise. Gold does not care about human pattern recognition. It responds only to energy, gravity, and time. A system can be perfect for gold accumulation and still look uninteresting. This disconnect is where gold hides in plain sight. One of the most common quiet failures happens when prospectors rely too heavily on surface signals. Surface geology tells only the most recent chapter of a much longer story. Gold, however, is loyal to older chapters. It remembers where it fell, where it stopped moving, where energy last failed to carry it any farther. If the surface has been reworked, even slightly, the visible clues may no longer align with where the gold actually rests. This is why quiet clues often appear below expectations, not above them. Consider a stretch of ground that shows no obvious mineralization, no bright veins, no dramatic coloration, no visual excitement. But the slope angle subtly decreases. The gravel suddenly becomes denser. The layering becomes more defined. To most people, this is meaningless. To gold, this is a stopping point. Energy dropped here, and when energy drops, gold obeys immediately. Another reason quiet clues matter is that they are resistant to fashion. Prospecting trends change. Certain rock types become popular. Certain methods get repeated. Certain signs become famous. But gravity does not follow trends. Quiet geological behavior remains reliable regardless of what people are chasing at the moment. This is why professionals who work for long-term yields pay attention to systems, not signals. A critical quiet clue is persistence of form. When a landform has maintained its shape for a very long time, it suggests stability. Stability allows sorting. Sorting allows settling. Settling allows gold to concentrate. Many experienced prospectors trust their memory too much. I've been here before. I already tested this area. There was nothing here. But quiet clues can change without changing appearance. A slight shift in water behavior, a subtle redeposition event, a small seasonal rework. Gold may arrive quietly after the first visit. The ground looks the same. The value does not. Another reason quiet clues outperform obvious signs is time compression. Obvious signs often indicate repeated movement. Flooding, erosion, exposure. Each event redistributes gold. Sometimes it enriches, often it disperses. Quiet environments experience fewer dramatic events. Gold settles once and stays. This is why boring-looking areas can hold gold longer than spectacular ones. It's important to understand that quiet clues are cumulative. One subtle signal means little on its own. But when multiple quiet indicators overlap, quiet clues often exist where no one bothered to document because nothing looked remarkable. Gold does not require documentation. It requires conditions. When you learn to value quiet clues, your behavior changes. You walk slower. You observe longer. You dig less, but more accurately. This alone increases efficiency. Efficiency increases recovery. Recovery builds confidence rooted in reality, not hope. The greatest advantage of quiet geological understanding is independence. You stop relying on rumors. You stop chasing what others are chasing. You begin trusting physical evidence instead of popular belief. This is where prospecting stops being luck-based. It becomes repeatable. And this is the point most people never reach. Not because it's difficult, but because it requires letting go of obviousness, letting go of excitement, letting go of the need for visual confirmation. Gold does not reward excitement. It rewards understanding. If you take one lesson from this entire video, let it be this. The quiet ground is not empty. It is simply unreadable to those who have not learned its language. Once you learn that language, the landscape changes permanently. You stop asking where gold might be. You start seeing where it must be. In the quietest corners of American wilderness, far from paved roads and phone signals, there exists a geological pattern so consistent that geologists almost treat it as a coded message from the earth itself. A message written in stone, whispered through time, and understood only by those who know how to read the land. They call it the three-rock combination, a natural lineup of minerals and textures so tightly connected to gold that whenever these three appear together, the likelihood of gold rises from possibility to near certainty. Most people walk through valleys and stream beds without noticing the clues lying at their feet. But gold is never random. It never scatters without logic, and it never travels alone. It forms, moves, and settles according to precise geological laws. Laws that leave unmistakable signatures behind. These signatures aren't obvious. They don't shine, they don't sparkle, and they don't call attention to themselves. But geologists have learned to recognize them as the silent fingerprints of ancient gold movement. And today, you will learn to recognize them too. Gold begins deep underground, born from mineral-rich fluids rising from molten rock far beneath the crust. As pressure builds and temperatures soar, microscopic particles of gold dissolve into superheated water, drifting upward through cracks, fractures, and faults. And as the planet cools those fluids, gold begins to precipitate out, sticking to the edges of the fractures, coating quartz veins, pooling inside breaks in the bedrock. This entire process leaves behind companions, rocks and minerals that form under the exact same conditions. When you understand these companions, you understand the entire Golden Trail. The first of these geological companions is a type of metamorphic rock that looks as though it has been pressed, heated, and folded by the weight of the continents themselves. Smooth, shiny, layered, and often glittering with mica, this rock records ancient heat and pressure stronger than nearly anything on the surface today. Geologists rely on it because this type of rock forms in the exact environment where gold-bearing fluids originate. It is schist, one of the most respected host rocks in American gold geology. Whenever you step into a region where schist appears, especially in mountain belts stretching from the Appalachians to the Rockies, you stand inside a zone shaped by the very same forces that produce gold. But schist alone isn't the signal. Gold needs a highway, something that carried the fluids upward and froze them in place. And for millions of years, that highway has been quartz. Thick white or translucent quartz veins cut through darker rock like frozen lightning. They slice across schist, granite, basalt, and almost anything in their path. When hydrothermal fluids carrying gold cooled inside these veins, they left behind crystals, fractures, iron staining, and sometimes visible flakes of precious metal frozen in time. Even the rusty orange-red stains that coat quartz in gold country tell a story. They signal iron oxidation, nature's way of marking the path of mineralization. Where quartz cuts through schist, the story of gold becomes clearer. But the real confirmation appears in a third rock, an often overlooked, heavy, rusty, metallic stone that forms at the surface when iron-rich minerals weather. It can appear deep brown, jet black, or blood red, and it leaves stains on anything it touches. This stone is ironstone, the unmistakable marker of a hydrothermal system that once pulsed with mineral-rich fluids. Gossan caps, iron crusts, limonite masses, and hematite-laced stones are nature's final stamp of approval. They say yes, the chemistry, the temperature, and the fluids that create gold were here. When schist provides the birthplace, quartz provides the pathway, and ironstone reveals the chemical transformation. The three-rock combination is complete, not a myth, not a rumor. A geological pattern repeated across the United States wherever gold has been historically and scientifically confirmed. From the Sierra Nevada range to the Georgia Gold Belt, from Arizona's iron-rich ridges to Colorado's metamorphic cores, From the river-cut canyons of Oregon to the ancient schist belts of Alaska, this trio appears with remarkable consistency. Finding these three rocks is like reading a coded map. First, you notice the schist, layered, glittery, easily split, shaped by immense heat. You run your hand across its surface and feel the grain of an ancient world. Then you notice the quartz, bright white, jagged, cutting across a darker rock like veins of frozen sunlight. And finally the ironstone, heavy, metallic, oxidized, a deep, rusty color that stands out even in the shade. These rocks are not random. Their presence together is a geological conversation, and each stone adds a layer of meaning. Gold hunters, prospectors, and professional geologists use this combination in the field without fanfare. They know that if schist and quartz appear together, the ground has history. But when ironstone joins the scene, the ground has potential. And when all three appear within walking distance, sometimes even within arm's reach, you have stepped into a zone where gold once moved, gathered, and concentrated. This is the exact method used in American exploration. Locating metamorphic host rocks, tracing the quartz veins that fracture them, and studying the oxidized ironstone that reveals the age of the system. Companies invest millions in drilling programs based on this geological triangle. Prospectors stake claims on ridges where these rocks intersect. And ordinary people, those who understand these quiet clues, find gold in places others overlook. When you walk into a landscape with these three rocks, you begin to see the world differently. Hills that once looked ordinary now appear as chapters in an ancient story. River bends become pathways that once carried broken quartz downhill. Rust-colored ridges become signposts pointing toward old veins. Even the gravel beneath your feet becomes a record of erosion, carrying fragments of the very rocks connected to gold. The power of the three rock combination is not just scientific, it is practical. It tells you where to look, how to interpret the land, and where gold is most likely to be trapped today. It teaches you that gold does not scatter randomly, but follows rock types, structures, and chemistry. And once you understand those patterns, you can predict where gold should be, even in places you've never explored before. Whenever you find yourself in a canyon, along a creek, or on a lonely mountainside in the American West or East, and you notice these rocks around you, schist whispering of deep origins, quartz marking the pathways of ancient fluids, and ironstone confirming the mineralizing conditions, stop for a moment. Look around. Listen to the silence, because you may be standing on the threshold of an area where nature once hid gold with deliberate precision, and the landscape around you is quietly waiting for someone observant enough to interpret it. The truth is that gold rarely reveals itself easily, but it leaves unmistakable hints in the rocks that accompany it. When you know how to read these hints, the wilderness becomes a geological map rather than a mystery. And this second part of the story begins with understanding what happens next, how to follow these rocks, how to interpret their placement, and how to transform geological clues into real discovery. Once you identify schist, quartz, and ironstone in the same environment, the next step is to determine how these rocks relate to each other. Geologists are trained to look for alignment, orientation, and the way veins intersect the host rock. When quartz veins cut across schist in clean, sharp lines, it means those veins likely formed during a period of intense hydrothermal activity. And hydrothermal activity is the engine of gold formation. These veins can run uphill, downhill, or across a slope, but they usually align with old fault structures, cracks in the earth that once served as pathways for mineral-rich fluids. By following the direction of the vein, You essentially trace the path that gold-bearing fluids once traveled. Ironstone plays an even more important role at this stage. Its presence does not just confirm mineralization, it reveals the age and exposure of the system. Ironstone typically forms when sulfide minerals weather and oxidize at the surface, which means the area you're standing in has undergone long periods of erosion. When these oxidized caps sit above quartz veins, they often point toward deeper, unweathered sections where gold can remain locked inside the rock. This is why some of America's richest gold finds have been made just beneath iron-rich hilltops. The rusty color is not just a stain, it is a sign of ancient chemical transformation. As you walk along slopes or creek beds in the United States, you may notice that these rocks appear in clusters. This clustering is not accidental. Water, gravity, and erosion naturally concentrate the fragments of these rocks together, especially near old volcanic belts and metamorphic terrains. When all three appear in creek gravels, it often means the original source is nearby, uphill or upstream. This is one of the most important clues prospectors use. Rocks always travel downhill, and gold, being heavier than nearly everything around it, tends to settle in predictable traps. So if you find these rocks together in a waterway, the next step is to trace their origin. Tracing uphill from a creek, following the fragments of schist and quartz, often leads you to the bedrock exposures where the original veins remain frozen in place. Along the way, ironstone scattered across slopes confirms that the ground has undergone oxidation and mineralization. Every rusty fragment you touch is part of a chain of evidence stretching back millions of years. And as the rocks become larger, more angular, and more freshly broken, you know you're getting closer to the source. American geologists often refer to this approach as reading the land, because the terrain itself is the text. The shape of the valley, the tilt of the hillside, the position of old boulder fields, all carry meaning. Gold-bearing areas frequently appear where steep slopes flatten, where ridges intersect like braided threads, or where old river channels changed direction long ago. If the three-rock combination appears in these zones, the probability of gold increases dramatically. Many of the best modern gold discoveries in the United States weren't found by accident. They were found by people who understood how to interpret rock combinations and follow them back to their origins. And it is here where the process becomes almost meditative. You take your time, you slow your steps. You observe the ground with calm curiosity. The wilderness becomes a quiet teacher. Small details begin to stand out. The sound of crunching iron-rich gravel under your boots. The distinct shimmer of mica from schist in the afternoon sun. The glint of white quartz between broken stones. You begin to sense a pattern. The environment feels mineralized, as if the land itself still remembers the ancient pressure, heat, and geological violence that once shaped it. When you reach the source area, whether it's a ridge, a hillside, or a bedrock exposure, you'll often notice the rocks aligning in a way that tells a story. Quartz veins may widen, ironstone patches may intensify, and schist layers may twist and fold in dramatic patterns. Sometimes you find broken quartz scattered downhill from a vein exposed high above. Other times you see rusty staining on the face of a rock wall, indicating that sulfide minerals once lurked inside. If you examine these surfaces closely, you may notice tiny fractures where gold once moved. Even if the gold is not visible, the structure of the rock carries the memory of mineralizing fluids. And this brings us to one of the most powerful techniques geologists use, examining contact zones. A contact zone is where two different rock types meet, such as the boundary between schist and quartz. These boundaries are prime locations for gold deposition because the change in chemistry and pressure often cause gold to drop out of solution. When quartz veins cut through schist and ironstone coats the edges of those veins, the chances of gold increase significantly. Many American gold mines began at these exact boundaries, but gold is rarely found at the surface. It is usually locked inside the quartz veins, trapped in fissures, resting in cracks in the bedrock, or broken off and carried into nearby waterways. This is why panning in areas with the three rock combination is so effective. If gold has eroded from the veins, it will settle into natural traps, behind large stones, inside cracks in the bedrock, beneath dense gravel layers, and in places where fast water suddenly slows down. These traps exist everywhere from Alaskan streams to Appalachian rivers. And because gold is so heavy, once it settles, it tends to stay put until major floods move it again.